The motivation for Lyapunov's direct method is the observation that if energy is constantly consumed in an electric or mechanical system, then the system will eventually settle down. In other words, the system state will enter an equilibrium point. Think, for instance, of a ball rolling down the side of a valley hill. It will roll up the other hillside, but not as high up as it started due to friction. Due to the friction, energy is constantly consumed, and the ball will eventually settle down at the bottom of the valley. This is an equilibrium point of the system. So if energy is constantly consumed, the system will eventually enter an equilibrium point. Based on this observation, the idea behind Lyapunov's direct method is that it may be possible to analyze the stability properties of equilibrium points by studying the energy of the system. Consider a two-dimensional system, since this is easy to visualize. Here is the phase plane. So consider a two-dimensional system which has an equilibrium point at the origin. The energy of the system is a scalar function of the state, and we will denote this by V. The energy of the system at the equilibrium point is 0. Now let us draw a line through all the points in the state space where the energy has the same constant value. Say that this constant value is C1, which is some positive value. We then get a curve in the plane which may look like this. Let us then draw another line through all the points in the state space where the energy has another constant value, C2, which is larger than C1. These curves are called level curves, or level surfaces in the general case where the system is not necessarily two-dimensional. These curves represent constant energy levels for the system. For all states on this curve here, the energy is constant and equal to C1. So how can we use this energy function to analyze the stability properties of the equilibrium point at the origin? Remember that we consider time-invariant systems in this form here, for which the origin is an equilibrium point. What we do is that we study the time evolution of the energy of this system. Specifically, we study how the energy evolves along the system trajectories. For instance, if the system trajectory moves towards level curves representing higher and higher energy levels, like here, then we see that this corresponds to moving further and further away from the equilibrium point at the origin, which should suggest that the origin is unstable. How do we compute the time evolution of the energy along the system trajectories? We simply take the time derivative of the energy function v. By the chain rule, the time derivative of v of x is the derivative of v with respect to x, which is the gradient of v, times the derivative of x with respect to time t, which is given by the system equation here as f of x. This is the directional derivative of the function v along the vector field f. It describes how v changes in the direction of the vector f, that is, how the value of the energy function v changes along the trajectories of the system. If this is positive, then the energy increases along x, as we see here. If it is negative, on the other hand, then the energy decreases along the system trajectories. This means that the system trajectories then intersect curves representing lower and lower energy levels until the energy becomes 0, which is at the origin. This we see indicate that the origin is an asymptotically stable equilibrium point. And note that we do not need to solve this differential equation to find x as a function of time t in order to see how the energy increases along x of t. The directional derivative of the energy function gives us this information. What then if the energy does not necessarily decrease, but it can also be constant? So its time derivative can also be 0. When the time derivative is zero, the energy is constant, meaning that the system trajectory moves along one of the level curves. So when the time derivative of the energy is either negative or zero, then we do not necessarily have convergence, but the behavior is similar to that of a stable equilibrium point. These intuitive observations that we have made here hold for mechanical and electrical systems, which have a well-defined energy concept. But how about general dynamical systems? Lyapunov formalized and generalized these intuitive observations in his doctoral thesis, The General Problem of the Stability of Motion, which was published in 1892. The theorems presented here, which constitute Lyapunov's direct method, hold for general systems, not only electrical or mechanical systems, for which we have a well-defined energy concept. Instead of the energy function, we must therefore use an energy-like function. And the question is, which properties must such a function have to serve as a generalized energy function, such that these intuitive observations hold, such that we can use it to analyze stability?